Hello everyone. Today we'll be discussing about a popular associative rule mining algorithm, also called as the a priori algorithm. In the end of the video, I'll also be discussing and analyzing the results which we find using this algorithm using a software called the RapidMinerStudio. So basically, what is this a priori algorithm? A priori is an algorithm for frequent item set mining and associative rule learning over relational databases. You may have all heard of relational databases while learning database knowledge. It proceeds by identifying the frequent individual items in the database and extending them to larger and larger item sets as long as those item sets appear sufficiently often in the database. The frequent item datasets determined by a priori can then be used to determine the association rules which highlight the general trends in the database. This is basically the purpose of this a priori algorithm. It finds its application in various domains, such as market-based analysis, where basically the collection of items which are bought by customers are analyzed using this a priori algorithm. It also has its applications in while collecting details of a website or while finding which IP addresses occur frequently. Other algorithms are designed for finding association rules in data having no transaction like WMAP or MINAP. But today we'll only be learning about this a priori. You may also have heard of DNA sequencing in which no timestamps exist. In that also we make use of a priori algorithm as I discussed in my previous videos. Each transaction is seen as a set of items. Now let us consider that we are given a threshold. The a priori algorithm identifies the item sets which are subsets of at least transactions in the database. A priori basically uses a bottom-up approach where frequent subsets are extended one item at a time. Each step is known as candidate generation, and a group of candidates are tested against the data. The algorithm terminates when no further successful extensions are possible. A priori also uses breadth first search and a hash tree structure to count candidate items sets efficiently. It generates candidate item sets of length from item sets of data. Then it prunes the candidates which have an infrequent subpattern. And also according to the downward closure lemma, the candidate set contains all frequent length item sets, after which it basically scans the transaction database to determine frequent item sets among the candidates. This is basically how our a priori algorithm works. Now, before moving on to a few examples, I would like to show you a snipe of the function, how basically the a priori algorithm looks like. This has been taken from Wikipedia. So I know it looks a bit complex, but once we solve a few examples, it will become clear. Now let us consider the following database where each row is a transaction, and you can see like each row, and each cell is an individual item of the transaction. Now the association rules that can be generated or formulated from this database are as follows. 100% of sets with alpha also contain beta. As you can see, all the 4 rows contains alpha, so does beta exist. 50% of sets with alpha beta also have epsilon. Similarly, 50% of sets with alpha beta also have theta. Like in the first and third row, alpha beta occurs alongside epsilon, and second 4, it occurs alongside the theta. Now we'll be moving on to an important example and tell how this a priori algorithm works. Let us assume that a large supermarket tracks sales data by stock keeping unit for each item. Each item, such as butter or bread, let us consider for this case, is identified by a numerical scheme. The supermarket has a database of transactions where each transaction is a set of SKUs that were bought through. So this is basically the database of transactions, and it contains the following item sets. What we'll be basically doing is we'll be constructing another table with an item and support value. This will be finding out how frequently these item sets, individual item sets, appear in this database. So basically 1 is appearing 3 times. As you can see, the first row, second row, and third row consists of 1. Similarly, for 2, the support value is 6, 3 is 4, and 4 is 5. Now, since we consider the value 3 as a support threshold, we'll be looking which support values are equal to or greater than 3. For this case, all of them have a value greater than or equal to 3. So we move on to the next step, where we'll now be plotting it in pairs. So the pairs which are possible for this scenario are 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. Similarly, we'll be calculating the support value that in which rows these following pairs exist. So the support values are given below. Now look carefully, there are two rows, 1, 3 and 1, 4, who have their support value less than 3. So we will scrap off all the item sets which consist of these two rows in our next step. And we'll only be considering the first, fourth, fifth, and sixth for our calculation. So you can see all the triplet values which are possible are 1, 2, 3, 1, 3, 4, 2, 3, 4. So we'll be scrapping the first two since it consists of the values 1, 3, and 1, 4. Here, 1 does not exist, so we can easily use this item set. Here also, you may notice that the support value is 2. So finally, we can conclude that in basically some items were not counted because one of the subsets was already known to be below the threshold, while the others are determined that the frequent sets of items in the database do not exist. Hence, this is how the a priori algorithm works. A priori algorithm definitely has its limitations as well. It is basically very inefficient because you may have noticed that if the data set is too large, it scans its database way too many times. Moreover, its time and space complexity is also a lot. I think it is around exponential, which is a very bad according to the programming level. So steps are also being taken to improve this algorithm, like MaxMiner, if you may have heard of, in which they are not using the bottom-up approach at all. Rather than they jump steps in that. As a result, it is producing and giving more efficient results. So this was basically what is a priori. Now we'll be moving on to the execution of our a priori algorithm. So basically, the dataset which I'll be using for today is Titanic dataset. Before we move forward, I'll be explaining what these panels mean. So this is basically a repository which stores a dataset. So I have just entered by default, you will see a lot of datasets in this. I have chosen the Titanic dataset with which we'll be performing our analysis. This is basically here you can select all the operators, whichever you want to use. And this is basically the help panel where once you click on each of the operator, it will give information about what the following operator does. These are basically nothing but the parameters which tell you about the operator. So first, what I have done is I've used the retrieve operator. As you can see, it is available after retrieving your Titanic database. Next, we'll be performing the FP growth. FP growth is necessary for carrying out your frequent items in the dataset. But we can't directly put those dataset in the FP growth algorithm because it only accepts binomial values. And you can see that these Titanic values are basically in CSV format, which are nominal. So what we need to do is convert these nominal values into binomial using this discretize function. So I'll just be showing you discretize. Here it is discretized by frequency. So this is basically what we'll be using to convert this nominal values to binomial. So once the data set gets discretized and converted into binomial value, and next, the FP growth moves this data into the create association rule, where we will be determining the association rules for our data set. So let me run the process. So this is basically where our association tools have been created. It basically shows you the support value and the confidence value alongside other data sets. Like Laplace game. These are basically the attributes, basically. So this is the PS value. This is the lift. This is the conviction. I'll be explaining one by one what each of it does. Support may be defined as the number of samples of the true response that lies in each class of topic. A confidence score is generally a number between 0 and 1, as you can see. That represents the likelihood that the output of a machine learning model is correct and will satisfy a user's request. Laplace, you all may have heard in, mostly used in statistics. Information gain is the reduction in entropy or surprise by transforming a dataset and is often used in training decision trees. Lift is a measure of the performance of a targeting model association rule at predicting or classifying cases as having an enhanced response measured against a random choice target. Conviction compares the probability. For example, let's say that X appears without Y if they were dependent with the actual frequency of the appearance of X without Y. This is how basically the conviction works. So lift and conviction are really important for this association. So as you can see, the conclusions that we get are the sex of the person, survive, and passenger fear. These are the premises, and the support values and confidence values are given. So we can select in each of them if we want to look at the values separately. Here, if you want to look at the separate values for conviction or PS values, basically shows you the highest top 3 or top 2 values. So that can also be found. Next is the graph. So this graph is a little bit haphazard, but this is basically how this association rule mining plots the graphs and tells you about how each attribute is associated with another. So this is basically the description. Now let us consider an example. Like if the attributes number of parents or children on board are existing, then passenger fear also plays an important role in determining the confidence value. That is how basically the association rule mining works. Similarly, like let us take this first one here, port of embarkation, which is the Southampton, survived patients, passenger class is third, then the sex of the person becomes then associated with these 3 attributes, and the confidence value is given as 0.80. So that is basically how this works. Now I'll be just showing you the parameters for each. Like this is basically discretized. This is not very important. This is nominal to binomial FP2. So here also basically you can check out the minimum support, minimum items per item set, maximum items per item set, maximum number of data sets, and so on. Here you can also look at the frequency. Here the given minimum frequencies. So here also you can list the items in a separate columns in a column according to your convenience in whichever way. This is the create association rules, and minimum confidence, as you can see, of our results is 0.8. Here the minimum criterion value for lift, and similarly for conviction, for PS, you can see all the values are almost 0.8. So that is how basically this is association rule mining for a priori algorithm works. I hope you understood the analysis and the data. Thank you.